Hi everybody. I wanted to take a quick minute in this video to discuss the concept of conjugation and aromaticity and the fine difference in how those two are related. We've already seen in our previous chapters the idea of conjugation, where we have two or more double bonds that are in adjacent positions along a molecule. And this is one example. What we need to remember here is that each one of these carbons, because it is sp2 hybridized, we have a free p orbital in each case. It can be represented, remember, as a dumbbell-shaped sort of a structure. And that double bond, remember, has to do with electrons that are overlapping and able to share between these adjacent p orbitals. Well, in this case, because we have overlapping p orbitals across the entire molecule, we could just as easily imagine that the electrons are free to roam, so to speak, in between any of those pairs of p orbitals. And so this molecule being conjugated has a special stability because those electrons are delocalized. In this case, these three pairs of pi electrons are delocalized across all 6 carbons in the molecule. And so this is an example of what we would call a conjugated, in this case, a triene, 3 double bonds. Now, in most of the chapter on aromatic molecules, we're going to be looking at benzene as our example. And benzene is a 6-membered ring that has 3 alternating double bonds like this. And so it's often drawn like this. It doesn't matter if you draw it with the double bonds in the 3 positions I chose or the other 3 positions, or if you want to be a little bit shorthand and sloppy about it, you can draw it as a circle like this. It's pretty common. This aromatic ring is maybe what you'd call the prototypical aromatic ring. This specific one is benzene. So we're going to see a number of things in this chapter. Some of them involve nomenclature of aromatic compounds. There's a little table in the early part of the chapter that lists a bunch of benzene derivatives. Unfortunately, you need to memorize those. Things like toluene is methylbenzene. Phenol is a benzene with an OH group attached. Anisole, aniline, benzoic acid, there are a number of these. Those are the parent names, essentially. And so when we see a more complex molecule that has one of those groups on it, we're going to need to know what the parent name is. And so you need to memorize those. There's no way around that. The book does go into this idea of what aromaticity is. And there are really 3 criteria, 3 factors that you need to look at with aromatic molecules, or to deem something as being aromatic, which is this special extra stable kind of example of conjugation. The molecule has to have a ring. Some books will say it has to be cyclic. It also has to have, I like the phrasing in our book, continuously overlapping p orbitals. Well, why is that important? Same idea that we had for the conjugated molecule. We're trying to delocalize these extra electrons across as much of the real estate as possible. So in order for a molecule to be aromatic, and I should maybe put that term up here at the top, we have to have a ring that consists of continuously overlapping p orbitals. That way, when we think about those electrons delocalizing, we can imagine them delocalizing around and around and around the ring, essentially not running into any obstacles. Furthermore, the pi electrons have to be, I always pronounce this name and wonder if I'm doing it correctly. I always say Huckel. If somebody is native to that language, you can tell me if I'm pronouncing it correctly. They have to be a Huckel number. This number has a simple formula. So we can say the number of pi electrons has to fit the formula for n plus 2. Importantly here, n is not the number of carbons. N is just an integer. And so these numbers of pi electrons are 2, although you're not going to find that in a molecule that's large enough to be a ring and fit the other criteria. We'd be talking about 6 pi electrons is the next one, 10, 14, and so on, so on, and so on. Of course, benzene, as our prototypical example, fits these criteria. It is a ring-shaped molecule, happens to have 6 carbons. All of those carbons are sp2 hybridized, and so if I were to add the atomic p orbitals like this, we can see that we do have this sort of constant overlapping around, all the way around, continuously overlapping p orbitals, and those orbitals are filled with a equal number of electrons, in this case 3 double bonds, or 6 electrons. There's going to be a number of questions in here that ask you to decide if a molecule is aromatic or not. Many of those are going to be carbon-containing molecules, and a couple of the examples are given here. We could talk about cyclopentadiene, which is given in the book as an example. This one does have a ring shape, of course, a 5-membered ring. Does it have continuously overlapping p orbitals? Well, it doesn't. And that's because this carbon at the top, if we draw in our extra hydrogens, we can realize that carbon at the top is sp3 hybridized. It does not have a p orbital, or a free p orbital. And so what we find out here is that these 4 carbons drawn at the bottom of this molecule are in fact conjugated to one another. This is a conjugated molecule, but it is not aromatic. So we would just simply say it is not aromatic. Okay, fair enough. If we were able to remove a hydrogen from this molecule, we could think about the molecule having lost a hydrogen, so the cyclopentadienyl anion. Now we have 1 hydrogen up here. We have a situation like this. And now we want to say, well, is this thing aromatic, right? Well, I don't know. Let's look at the criteria. 1, ring-shaped, yes. 2, do we have a continuously overlapping set of p orbitals? Now we need to think about this a little more carefully, and it relates to some of the discussions in the previous chapter about conjugation. Ordinarily, if I were to present you with an atom like this top carbon, and I were to say, what's the hybridization of that carbon? A carbon with 3 bonds and a lone pair of electrons. You would count up 4 electron groups, and you would say, well, that's sp3 hybridized. However, if we imagine that this carbon was reconfigured such that that pair of lone electrons was in a p orbital, if we imagine that that top carbon were allowed to be sp2 hybridized to account for its 3 bonds, and we were to imagine putting those lone pair of electrons into a p orbital, now we do have this continuously overlapping set of p orbitals. And furthermore, we have a Hückel number of 6 pi electrons. That's our lone pair, gives us 2 electrons, and our 2 double bonds gives us a total of 4 more electrons. And so this is aromatic if that top carbon is sp2 hybridized. Now, the advantage here, the energy savings in being able to delocalize the electrons from the conjugated positions all the way around the ring is so significant that that carbon does in fact occupy an sp2 hybridization state. And so that carbon is sp2 hybridized. This molecule is aromatic. The other example that's sometimes discussed in the textbooks is what would happen if I were to take off a hydrogen with its electrons. And so we get the cyclopentadienyl cation. Well, what now? You'll see different examples in the book. We can think about this in the same way. Okay, now what's the hybridization of that top carbon? Well, now it's obviously sp2. It has 3 groups of electrons. That's sp2 hybridized. So it does have that empty spot, the p orbital, that is available to it. It's sp2 hybridized. So now we want to think, is it aromatic or not? Well, what does it mean to have a positive charge in there? It means that there are no electrons in it. So essentially think of it as an empty p orbital. And so yes, it's a ring shape. Yes, it has continuously overlapping p orbitals, but now we only have 4 pi electrons in that system. So sure, they can delocalize, but it's 4. That's not a Huckel number. And in fact, this molecule is something we call anti-aromatic. Anti-aromatic molecules are those where the number of pi electrons equals 4n, not 4n plus 2. So these would be 4 or 8 or 12, so on, or n is an integer, remember. So what's the difference between these 3 terms? Well, not aromatic just means it's not aromatic. It might be something else. It might be conjugated. This isn't even a discussion about aromaticity. Aromatic means it's extra stable. And so in practical terms, it will be harder to react with that molecule. In this case, this particular example of losing a hydrogen ion to get to this point, that tells us that that hydrogen will come off more easily. It's going to be more acidic than we would normally predict. And in fact, in this particular case, normally removing a hydrogen from a carbon, that would have a pKa of something in the order of 50 to 60. It's practically impossible to remove a normal hydrogen from a carbon. In this case, the pKa is down around 16, which is kind of more like the pKa of an alcohol. It's so much easier to remove that hydrogen because the resulting base, the anion in the middle there, is extra stable. And so since it is so stable, it's easier to form. Thus, it was easier to remove that hydrogen. The bottom case, when we see a molecule that is anti-aromatic, that means that it is particularly reactive. It is less stable, and so less likely to form than normal. It's not the same as not aromatic. It's actually worse than that. It's anti-aromatic. The last thing I want to say in this video, in talking about the idea of aromaticity, is that although most of the examples that we talk about are carbon-based molecules, and in fact most of them are benzenes, we're going to see a section that talks about aromatic heterocycles. So molecules that are aromatic that do not have all carbons. And a couple of the classic examples that are described in every textbook, including our textbook, are pyridine, which is a 6-membered nitrogen-containing heterocycle. It has double bonds like so. And just for the sake of our discussion, I'm also going to pencil in the lone pair of electrons that we know must be on that nitrogen, right? 4 groups of electrons. This molecule is pyridine. And the other molecule that we could talk about is Pyrrole. Pyrrole is a 5-membered nitrogen-containing ring that looks like that. It has a couple of double bonds here. It's typically drawn protonated. And again, I'm going to pencil in the lone pair of electrons. The big question when we talk about these other molecules, these heterocycles, is what do we do with those lone pair of electrons? Where are they? Just like we talked about the cyclopentadiene a minute ago, where are the lone pair of electrons? What kind of orbital are we talking about? What kind of hybridization do we have for the heterocycle? And so let's look first at pyridine. And let's think about pyridine and what's going on. Well, what's the hybridization of that nitrogen? If we were to look at the hybridization of a nitrogen like in pyridine, we would say that's a nitrogen with 3 groups of electrons around it. So it has a double bond, a single bond, and a lone pair. That nitrogen is sp2 hybridized. Okay, great. We would have gotten that from Gen Chem. The question is, where are those lone pair of electrons? Are they in a hybrid orbital, or are they in fact in the atomic p orbital that's left over? That impacts how many electrons we have in our potentially aromatic system. right? We already see that this molecule is a ring shape, so it satisfies criterion 1 for aromaticity. We now have determined that the nitrogen is sp2 hybridized, which means that there is a leftover p orbital, which is great. And does it overlap, right? Is it part of the system? And how many electrons are there? So what we want to think about is the nitrogen's p orbital already evidently used somewhere? And it is. It's right here in this double bond. That double bond is the result of the carbon's p orbital overlapping with nitrogen's p orbital. And so when we look at that particular bond right there, that's the carbon's p orbital overlapping with the nitrogen p orbital. Well, that means that the other bonds here and here are the result of carbon's sp2 orbital, hybrid orbital, overlapping with the nitrogen sp2 hybrid orbital, both of those green ones. And in fact, then, running out of colors, I guess I'll stick with green. And in fact, that means that this lone pair of electrons is in nitrogen's third sp2 orbital. So I've got my sp2s drawn in green. I've got my, sorry for that, my p orbital overlap drawn in red right there. And so those two electrons are in the p system, the pi system, as are those two, and as are those two. So we've satisfied the ring shape, we've satisfied the overlapping p orbitals, everything's sp2 hybridized, which is great. We also have 6 pi electrons, which is a Heckel number, and so yes, this molecule is aromatic. Pyridine is aromatic. Now, if we look at Pyrrole, as the other example, we see a similar kind of a situation. We see a pair of electrons on a heteroatom, on a nitrogen in this case. We want to do the same kind of analysis, okay? So what's the hybridization on that nitrogen? Well, on first glance, we'd say sp3. It has 4 groups of electrons around it, 3 bonds, and a lone pair. That's 4 groups, sp3 hybridized. But, just like we saw on the previous slide, if that nitrogen is sp2 hybridized, then we could think about having an aromatic system here. That extra stability is something we have to give a second look. So let's pretend for a second that the nitrogen is sp2 hybridized. Now, where are those sp2 hybrid orbitals? So I'll try to use the same color coding I used up above. I've got 1 bond here and 1 bond here. Those would be my carbon sp2 orbitals overlapping with the nitrogen sp2 orbital. And I've got 1 here. Well, how do I know? That hydrogen doesn't have a p orbital, right? Hydrogen's too small. What I'm looking at here is nitrogen's third sp2 orbital overlapping with hydrogen's 1s orbital. And so I'm left with now an extra pair of electrons that could potentially be in nitrogen's leftover 2p orbital. The 2 there is only because it's period 2, right? Don't get confused there. It's just a p orbital. The carbons over here and over here have overlapping pairs of p orbitals. And so if I think about that nitrogen being sp2 hybridized, and I think about those pair of electrons being in the p system, now I've got, again, a system with ring shape, continuously overlapping p orbitals, and a Heckel number of electrons, also aromatic. We could do the same kinds of discussions when we talk about molecules that have sulfurs or oxygens, nitrogens, or sometimes both. The key thing here is you want to draw out the lone pairs of electrons first. So don't forget to do that. Once you have the lone pairs of electrons drawn, then think about, what do I think the hybridization of this molecule or this atom is? And if it was a little bit different, if it was, say, one step down here, sp2 instead of sp3, for instance, does that buy me the extra energy savings of aromaticity? If it does, then you can draw it out that way and see what you get. So there are lots of problems. There's an entire skill builder exercise in our textbook that talks about whether a lone pair participates in aromaticity. I'd encourage you to look at that one, read through the examples, practice it, check your answers in the solutions manual, and get kind of some practice on this topic. So that's it for this video. Good luck, and I will talk to you all again later. Thanks.